let's talk about covalent bonds. So with molecular compounds, the Lewis structure is going to show the neighboring atoms sharing electrons to make octets. For hydrogen, it's just a duet because it's got to be an exception to everything. So let's look at the bonding in water and in a chlorine molecule. So we're going to start out with the element symbols and make the Lewis symbols out of those. So here's oxygen. We already did this one. Come on. So 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electrons. How many valence electrons does hydrogen have? 1. Uno. It only has 1 electron. So there's 1 hydrogen. Well, this oxygen wants 8 electrons. Hydrogen wants 2. So oxygen's trying to convince hydrogen, give me that electron, I want it. And hydrogen's like, I may be small, but I'm not giving you my electron. No way. You give me one of yours. You've got more. You could spare some. They'll argue about this and never come to a conclusion. So if nobody's willing to give it up, then we need to share. So hydrogen and oxygen reach a compromise by sharing. So let's just connect the dots and say that those 2 electrons are being shared. When something is shared, it belongs to both people, right? My husband and I share 6 children, right? They're mine and they're his, but that doesn't mean there's 12 of them. Thank goodness, there's only 6. Although now that James is engaged, I don't know what that does to the, I don't know how that changes the effect, but they're not married yet. So hydrogen counts both of these electrons as belonging to him. So hydrogen's cool. Hydrogen's happy. Great, I got my duet. The oxygen, though, is like, well, this is better, but I only have 7. So we're going to look for, I didn't mean to do that, look for another hydrogen atom. Not too hard to find. There's another hydrogen atom with one valence electron. And so hydrogen and oxygen will share. There's some serious problems here with my stylus. And so now this hydrogen is happy. It's got its duet. And oxygen counts all of those electrons, and oxygen's happy too. This is how nonmetals obtain octets. So before we get to chlorine, it says identify bonding pairs and lone pairs or non-bonding electrons. So this pair of electrons is a bonding pair. It's forming a bond between oxygen and hydrogen. And this is a bonding pair. Right? So these guys are bonding pairs. There are also some electrons here that are not involved in bonding. These 2 electrons sitting on oxygen are not bonding with anything. We call them a lone pair. And this is a lone pair. We tend to refer to them as lone pairs as opposed to non-bonding electrons because it's just easier. So lone pair. And the number of lone pairs and bonding pairs has a big effect on some things like shape of the molecule and the polarity and all kinds of other things. And so that'll be important later. So let's do chlorine. How many valence electrons does chlorine have? 7. So 1, 2, 3, 4, 5, 6, 7. And here's oops. Here's the oops. There's another one. 1, 2, 3, 4, 5, 6, 7. With potassium, sodium just took potassium's electron because metals will do that. They'll just, hey, you just take it. I don't want to share with you. You just take it and go away. Oh, but now that you've got this electron, I'm really attracted to you. Really funny thing. But 2 chlorines why would one give an electron to the other? They wouldn't. And so they're going to share. So they're going to each share that one electron that isn't paired up. And they can count the shared electrons. So this chlorine has 7, and this chlorine has 7. The circles are not part of the Lewis structure. So how many bonding pairs in this molecule? 1. How many lone pairs? 6 in the whole molecule. There's 3 on this one chlorine and 3 on the other, so a total of 6 lone pairs. So you should be able to identify bonding pairs and lone pairs. Any questions? This is a single covalent bond. A single pair of electrons is being shared. But you can share more than one pair. So let's look at oxygen. It has a double bond, O2. So there's oxygen, and here's another oxygen. Let's do the electron business. So they each have 6 valence electrons. And there's nobody else around for them to share or transfer with, and so they're going to seek out each other. It's like, how can we do this and get 8 valence electrons each? So, well, let's share a pair of electrons. Well, this is nice, but this isn't good enough. So they're going to share a second pair of electrons. So sharing 2 pairs of electrons is a double bond. So this is kind of an awkward picture. It actually looks kind of like a face.
Almost like you connect the dots of a koala or something.
Yeah. You could do all kinds of things there. So this is how we usually do it. We draw 2 lines. Those are the double bonds, and then we stick the lone pairs out here. You can put them however you want. So this is the Lewis structure for oxygen. When we draw some circles, we see that, okay, so this oxygen has 8 valence electrons, 2, 4, 6, 8. And the other one also has 2, 4, 6, 8. So the line in a Lewis structure represents a pair of electrons. And it might be helpful to think of it as those 2 electrons connected. So anytime there's a line, there's a dot at each end, whether it's written or not. Any questions? So let's look at nitrogen. How many valence electrons? 5. 1, 2, 3, 4, 5. And another nitrogen atom. 1, 2, 3, 4, 5. Well, let's share this pair. Do we have 8? 8 valence electrons yet? No. Let's share another pair. Make a double bond. Are we there yet? Nope. Got to share a third pair. Okay? So nitrogen forms a triple bond with another nitrogen atom. And we would normally draw that like this. And put the lone pairs over here. So this nitrogen counts 2, 4, 6, 8, and this nitrogen counts 2, 4, 6, 8. There's a lot of counting by 2s in making Lewis structures. Any questions? Triple bond. See, this is what my husband and I have. Ooh, well, no, that's not going to work either. But anyway, there's James and Zach and Tommy and Michael and Andrew and Emily. We didn't do it that way on purpose. We only wanted a double bond. Okay, so how does the Lewis model predict stability? Well, H2O is a stable molecule. H3O is unstable. Let's look at their Lewis structures. We've already done water, and so I'm not going to go through how to do it again. I'll just draw it in here real quick. So there's water. Now, if we're going to do H3O, so there's H2O. H3O, we have to put another hydrogen on there. So here's another hydrogen with its 1 electron. it's not going to go over to this hydrogen and try to share with that, because this hydrogen's already sharing with oxygen. It's really happy. It's not going to do anything. It doesn't have any lone pairs or anything else it can offer. So this hydrogen's going to approach the oxygen and say, hey, hey, share with me. Well, if oxygen shares with hydrogen, what happens to oxygen's octet? Now it's got 9. More is not better. More is just more. They're going for 8. Not 9 or 10, not 7, 8. So this is not stable because it doesn't have an octet of electrons for oxygen. Well, what if we had H3O plus? How would we get a positive charge on this thing? Lose an electron, right? Well, let's get rid of this one. Now we've got a charge on this, but does oxygen have an octet again? It does. 2, 4, 6, 8. Each of the hydrogens has a duet, and so the Lewis model predicts that this is a stable ion, and it is. What about H2O2? There's the Lewis structure for hydrogen peroxide. Do each of the oxygens have an octet of electrons? Yeah, they do. 2, 4, 6, 8. 2, 4, 6, 8. Each hydrogen has a duet. Lewis model predicts that hydrogen peroxide is stable. And relatively speaking, it is. So the nice thing about the 4 and the 8, right? So we have 4 positions, top, bottom, left, and right. 2 electrons in each position gives you 8, which is like the magic number. Any questions? I'm so glad it wasn't 5 and 10 because that would just be so much harder to draw. Well, does this match up with reality? Covalent bonds are highly directional. Let's go back to way back here. Way back here, these guys. So this is the lowest potential energy when that electron that's being shared is between the nuclei. If you pull it over here, you pull it over here. I kind of think of this as being like a rubber band between these two things. And if you pull it up and let go, what happens? It snaps and it goes back to this. If you pull it over here and let go, it's going to return. That's the stable position. This bond is highly directional, and it is just between 2 atoms. Unlike ionic bonds, opposite charges attracting each other in all directions. Okay, now I have to get back where I was. So the covalent bonds are highly directional. That's why covalent compounds have molecules. In an ionic compound, you've just got this alternating lattice of oppositely charged ions, and they attract each other all throughout the whole thing. Molecules are what covalent compounds have. Well, there's obviously something attracting the molecules to each other. Like, water is a liquid at room temperature. There must be something holding those molecules together. But it's not as strong as a bond. And so those weak forces between the molecules give molecular compounds lower melting points. Some of them are gases at room temperature, liquids at room temperature, or they melt very easily. Sodium chloride can be made to melt, but it's over 1,000 degrees Celsius. It's like crazy, crazy hot.